So adding on and building off of our composition functions, our algebra functions, we're going to be looking at inverse functions. So I talked a lot last time about temperatures, Fahrenheit conversions to Celsius, Celsius conversions to Kelvin, how we can use composition to come up with an equation that converts from Fahrenheit directly to Kelvin, okay? And the way that relationship works is if I take a temperature in Fahrenheit and I convert it to Celsius, I say, okay, 68 degrees Fahrenheit equals 20 degrees Celsius. I can also work backwards and say, well, if I have 20 degrees Celsius, what degree Fahrenheit is it? And it always points back to the same value. Every degree Fahrenheit corresponds with exactly 1 degree Celsius. Every degree Celsius corresponds with exactly 1 degree Fahrenheit. So what that does is that makes a very special type of function where we have a one-to-one relationship. One-to-one means that every single input corresponds with one y value, which is the definition of a function. Every x value corresponds with one y value. But in order for it to be a one-to-one relationship, the same has to be true in reverse. Every y value corresponds to exactly one x value. When we first talked about functions, I gave an example about test scores. Emmy and Jelly can both get a 90 on a test. Okay, so the input is the student, the output is the test. They're both allowed to get the same score. Okay, Lourdes can also get a 90. Ari can also get a 90. As many inputs of students can get the same score. Doesn't cause an issue. But if Jelly got a 90 and an 85, that doesn't work. That doesn't make sense. It's not a function if Jelly can get two different outputs on the same input. Okay? So that's the definition of function. Every x value corresponds to one y value. Okay? But if everybody or multiple people get the same output, it's not a one-to-one function. That output isn't unique. In order for it to be a one-to-one function, the output also has to be unique to every single input. Okay? So for example, the students and the seats you are sitting in. There's not two students in one seat. There's not two seats for one student. Every student has one seat. Every seat has one student. Okay? That's a one-to-one relationship. So when we have a function that follows this, we have a one-to-one function, and there's a lot of implications that build on that we're going to look at. So the first thing we want to do is kind of look at a bunch of different representations and determine whether or not we have a one-to-one relationship. So when we look at a set of ordered pairs, we want to make sure that first part is true, that every x value corresponds to one y value. And so I can look at my first set and I say, okay, I've got all my x values of 1, 3, 5, and 6. And then I have my y values of 2, 4, 6, and 7. And I can see that 1 corresponds to 2, 3 corresponds to 4, 5 corresponds to 6, and 6 corresponds to 7. Every x value matches up with its own y value. Matches up with one y value. And the reverse also has to be true. That every y value points to its own x value. There's no crossover. That's how we determine whether or not we have a one-to-one function. None of the x values repeat. None of the y values repeat. One-to-one. None of the x values repeat. None of the y values repeat. When we look at our g, our next function, we can look at the ordered pairs. And we can say, okay, I've got x values of 0, 3, 6, and negative 2. I have y values of 3, 7, and negative 2. And I can draw the relationship. 0 points to 3, 3 to 7, 6 to 7, 2 to negative 2. So it's still a function. Each x value points to one y value. Okay? I take an input, I get one output. But when we do the reverse, 3 points to 0, but 7 points to both 3 and 6. So because of that, it's a function, but it's not 1-to-1. You have a function, but it's not 1-to-1 because one of our y values points to 2 different x values. Not a 1-to-1. Let's look at our chart. We have 5 different types of mineral. Those are our inputs, and we're measuring their hardness on a scale. Those are the outputs. So take a look at that and think about, is it 1-to-1? And why? Or why not? Look at the mineral to the output. Does every input correspond with one output? Output correspond with only one input. So both of those? Why? 2 shows up twice on our output. So think of it this way. If I ask you a question about an input, you give me one number for an output. Okay? I could say, what's the hardness of talc? 1. What's the hardness of gypsum? What's the hardness of diamond? What's the hardness of topaz? And the hardness. Each of those has one output. But if I go in reverse and I say, which mineral has a hardness of 1? Talc. Okay? There's only one answer. Which mineral has a hardness of 2? And stiffness. Because there's 2 answers, it's not 1-to-1. There's 2 answers for one number, it is not 1-to-1. Let's look at our graph. 1-to-1 or no, and why? Why? Y value. Here, here, and here. So if I asked you the question of what x value has a y value of 1, you'd have to give me 3 answers. So it's not 1-to-1. Not 1-to-1. Still a function, it's just not a 1-to-1 function. We used to, earlier in the year, we covered a test that we used to evaluate whether or not a relationship was a function. Does anyone remember what that test was called? Vertical line test. Okay? Vertical line test says, hey, if I take a vertical line and I run it through, as long as I never touch more than one point at a time, I have a function. So I can see function, 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 function. We're good. Now we also have that assuming that something passes the vertical line test, we can also check to see if it's an inverse, a 1-to-1 function, if it passes the horizontal line test. And if my horizontal line only ever passes once, more than once, then that's how we can visually see a graph as not 1-to-1 because it fails the horizontal line test. So we can look graphically and say, okay, well, let's first determine, is it a function? And if it is, does it pass the horizontal line test? If a horizontal line intersects the graph of a function, again, assuming that it's a function, at most once, then it is a 1-to-1 function, meaning that none of the y values repeat, none of the x values repeat. So we can look at each of these graphs and say, okay, all right, one at a time. So we'll look at our red graph. Is it a 1-to-1 function? Yeah. Doesn't ever touch more than once. We could do the vertical line test as well, and it's never going to touch more than once. So we know it is a 1-to-1 function. Oh, I get funky with the colors. All right. 1-to-1 All right? We have a quadratic here. Parabola. Why not? So horizontal line test. Is it a function? It's still a function. Passes the vertical line test. Just not a one-to-one. Not one-to-one. Okay? We have a cubic function in green. One-to-one? Depends on how the cubic works. Sometimes they are, sometimes they aren't. This is just a basic x cubed. So while it gets really, really close and levels out there, it's only 1 point at any given time on a horizontal line. So it is still one-to-one. No, because some cubic functions get really funky and do that. And at that point, now it's failing the horizontal line test. So the only time it's going to be one-to-one is if it doesn't do those funky waves. But if it just levels out and then keeps going at that bend, then it's going to be one-to-one. What about our last one?
Yeah.
What'd you say, Emmy? It's not a function. How do you know? Fails the vertical line test. It passes the horizontal line test, but that's moot because it fails the vertical line test. Not a function. So it can't even be one-to-one because it's not even a function to begin with. It fails the vertical line test. Okay? Is it a function? And if so, does it pass the horizontal line test? Now, once we've identified that they're one-to-one, we have this relationship called inverses. Any one-to-one function, we can find its inverse by switching the x and the y coordinates. Switch the input and the output. So when I'm looking at conversions of Celsius and Fahrenheit, I can convert from Fahrenheit to Celsius by inputting a Fahrenheit and I output a Celsius. And then I can do the opposite, where I take a Celsius and I plug it into a formula, and I get an output of a Fahrenheit. Because they're one-to-one, those relationships, those conversions are inverses of each other. So going from input to output, and then the inverse is going back from output to input. Given whatever function we have in function notation, we notate its inverse through f of -1 or g of -1 or p of -1, whatever our function is. We call that f inverse or g inverse or h inverse, whatever it is. In function notation, we can have f of x. In function notation, we can have f inverse of x. Okay, it's not an exponent being applied. It's just a notation for this is the inverse. And we see that in other mathematics later on, especially with trigonometry. We'll see things like sine of x and the inverse sine of x. Same kind of an idea. It's just a notation dictating, hey, this is the inverse. We're not applying a mathematical operation to it. When we switch the coordinates of ordered pairs, because we're changing the x and the y, since domain represents all the x values and y represents range represents all the y values, when we switch x and y, we're also switching domain and range. So domain and range will switch. If I have an ordered pair on one point, I can switch the coordinates and I have an ordered pair for the other function. So we can see that relationship back and forth. We can see that on our diagram. If I have an input of 13 degrees Fahrenheit, I get an output, negative 13 degrees. I get an output of negative 25 degrees Celsius. That gives me the ordered pair, negative 13, negative 25. If I switch them, that gives me an input of negative 25 and an output of negative 13. It gives me a new ordered pair that is on the inverse. All right, so we can take a function with a list of ordered pairs, and we can find the inverse of that function by switching the coordinates. So we have our function g. We can find our inverse of g by switching the coordinates of each ordered pair. If I switch the coordinates of 3, 4, what do I get? 4, 3. So the inverse will have the point 4, 3. What about for 6, 2? 2, 6. What about for 2, negative 3? Negative 3, 2. And then what about for 4, negative 5? Negative 5, 4. Easy peasy, right? Switch the ordered pairs, and that gives us our inverse function. I can do that on a graph as well. If I have a graph with a bunch of points on it, I can write those coordinates, switch those points. Now I have my inverse function. Okay? Switch the coordinates for the ordered pairs. Now, if I want to find the equation, the idea is the same. The process is just a little more involved. We're going to switch x and y out of the equation. So we're going to take our function and replace it with y. So we have a simple equation, either linear or nonlinear, doesn't matter. The idea is still the same. And then we want to interchange the x value and the y value. Where there's an x, I'm going to replace it with a y. Where there's a y, I'm going to replace it with an x. The 6 does not move, the negative 1 does not move. X equals 6y minus 1. All I did was switch the x and the y. Then we want to get it back into standard form, so we're going to solve for y. What can I do to get y by itself? Add 1, and then divide by 6. So we get y equals 1/6 x plus 1/6. And then we want to go ahead and return it back into function notation. But since we found the inverse, we're going to write it as f inverse of x equals 1/6 x plus 1/6. So we've got the inverse equation. There's a very special relationship between functions and their inverses when we look at them graphically. So let's start with graphing f of x. Okay? Let's see if you guys remember how to graph a linear equation. Where should I start graphing the line y equals 6x minus 1? Where should we start? Zero, negative 1. Okay, so I have the point 0, negative 1. How do I get my next point? 1, comma 1. How do I get my next point? We're still on this one. We're graphing y equals 6x minus 1. I'm starting at negative 1. How do I find my next point? What do we call that 6? Slope. So how do I use my slope to get from here to my next point? 6, right, 1. What's that ordered pair? 1. Okay, and then we can draw our line. There's my ruler. There's my ruler. So we can draw our linear equation. I want to try and get this as exact as I can so the graph looks better. Okay. So we've got our line, pretty close there, for f of x. Okay. Now let's graph the inverse. Where do we start? Where's our y-intercept? 0, 1, 6, right? Okay, how do I get to my next point? Yep. Rephrase that again. I mean, a line goes in both directions, so it's just whatever the slope tells us. Oh, I didn't go 6. There we go. Too far. There. All right. Much better. All right, so we can connect that line. All right. So we connect those points. Now, this point is 0, negative 1. What's this one? This point is 5, 1. What's this point? What do we notice about those points? They're inverses. The x's and the y's are switched. And that'll be true for every single point on that line. If I have the ordered pair 0, 1, 6 right here, on my inverse function, I have to have the point 1, 6, comma 0. Every single endpoint and its inverse will match on that line. So if I have the ordered pairs for one point, I can change the coordinates and graph the other function, which may be easier in this case because it's a whole lot easier to graph negative 1, 0 than it is to graph our y-intercept. Other thing that every single inverse function has as a relationship. Where's my angle? 45 degrees. Right there. If I take the equation, the line, y equals x. Straight line with a slope of 1 that passes through the origin. And I compare each point and its inverse to that line. They are always going to be the same distance from that line. So we have symmetry with inverse functions about the line y equals x. They will always be equidistant from that line, every single point on that curve. So that's also a visual way that we can identify whether or not a function is likely to be the inverse of graphically if we have that symmetry. And we can pick points on both curves and we should see that symmetrical relationship. But those distances will always be the same from inverse to inverse. They will always be the same. Let's go ahead and do the same thing with g of x. What do I do first? We're going to replace g of x with y. And then when I switch them, what's my new equation? Good. Now what? Yep. Do what? Add 5. Divide by 3. Now what? G inverse of x. Okay, so let's graph our original function first. G of x equals gx minus 5, or 3x minus 5. Where do I start? 0, negative 5. 0, negative 5, and then where's my next point going to be? Okay, which is what ordered pair? And we could keep doing that and keep filling in those points. So I've got 0, negative 5, I've got 1, negative 2, I've got 2, 1, and I've got 3, 4. There's my line. So we can draw our line, connect our points. Now, given those points, give me one point that's going to be on my inverse graph. So 1, negative 2 is on this one. You said, say it again, Jelly? Give me another one. Give me another one. Oh, negative 2, 1. Is that? I misheard. Give me another one. 4, 3. If I have my inverse function, all those points and their inverses should be on my new line. And we can check it with our equation and make sure that it matches up. So we'll go ahead and connect these dots and we'll compare the line to our equation. Yeah.
So say we do that, right? And then we were to do the first intercept with the 5, 1, 3.
So that's just an easier way to graph it. And what I'm going to do is I'm going to compare it to this equation. I'm going to say, okay, I should have a y-intercept of 5/3. Yeah, and I look and say, oh, yeah, that's about right. And a slope of 1/3. If I go from here, up 1, right 3, up 1, right 3. All of that checks out so that we can use those as a tool to make sure that our equation matches up and our graph matches up. And we can also see the symmetry about the line y equals x. Those points are equidistant apart, those points are equidistant apart, those points are equidistant apart, and those points are equidistant from that symmetry line. And so we can see visually in a couple different ways that the points actually match up the way that they should. Last thing I want to talk about is mathematically verifying whether two functions are inverses of each other. Because of that symmetry with the line y equals x, that's actually a side effect of composition. If I compose a function into its inverse and the inverse into the function, and it always simplifies to give me x when I do both of those, mathematically, that's how we see that symmetry, and we can verify that they are inverses of each other. So we can do f inverse of x, and we can also do f of f inverse of x. And if they both equal x, then we know they are inverse functions of each other. Now, before we do the first example, what I want to note is this is a little bit of a typo. That should be over here, so fix that on yours, because that's part of that example. So I'll move that over, and I'm going to erase that. Get rid of that. There we go. Solved. And let's give myself some space here. Okay, so we're going to start with doing each composition. So we have f of x is 3x plus 2. We have f inverse of x minus 2 over 3. We need to do both compositions. So we want to take f inverse and we want to plug it into f of x. So f inverse is x minus 2 over 3. And we want to compose it and drop it into our first function. So we get 3 times x minus 2 over 3 plus 2. What's the first thing I can do to simplify here? Okay, so we have 3 times x minus 2 over 3 plus 2. Now, yeah, the 3's cancel out, right? 3 divided by 3 is 1. So we're left with x minus 2 plus 2. And then what's minus 2 plus 2? 0, so it's just x. Negative 2 plus 2 is 0. Those cancel. We're left with just x. Now we want to do it again in the other direction. Okay? So we want to take f inverse of f of x. And f of x is 3x plus 2. So we're going to plug it into our inverse. 3x plus 2 minus 2 over 3. Now what? Yep, so we're left with 3x over 3. So we're left with just x. So that means that f of f inverse of x equals f inverse of f of x, and they both equal x. Therefore, they are inverse functions. We are verifying that they are inverses. Do the same thing for b. We do the composition, and we start with f of f inverse. F inverse is the cube root of x plus 5. So we want to plug that right into our original function. If I take the cube root of x plus 5 and I cube it, what happens? Leaving me with x plus 5 minus 5, which equals x. And then same thing, we do our inverse. And we want to plug in x cubed minus 5 into our cube root function. So we get the cube root of x cubed minus 5 plus 5. What do I do next? What do I do before that? Negative 5 and 5 cancel, and then that gives me x. And so they are inverses based off of the same reason that we have here. They are also inverses of each other. Wow, that did not work as well at all. Copy, not as text. There we go. Perfect. Okay, so there's our composition of functions. When you're doing your composition to verify inverse, if the first one that you do does not give you x, you don't have to continue. You already know they are not inverses of each other. But when you do the first one, if it works, you still have to check the other one. There are some cases where one composition will simplify to x, but the other one will not simplify to x. So you need to verify both. Questions, comments, related to the lesson.